Vectors. So, what are vectors? Vectors are mathematical objects with both magnitude and direction. There are two ways to represent vectors. One, we could represent what I call the geometric representation. So here we draw the vector and give its length or magnitude and an angle. So here we gave the angle theta, which is the angle that you would get if you wind up from the positive x-axis moving counterclockwise. Although the geometric representation is more common in physics, in mathematics we use the component representation. And with the component representation, you, rather than giving the length and angle, you give the length along a certain axis. Here's the x-axis, and the length along the x-axis is u1, and the length along the y-axis is u2. And these numbers could also be negative. Of course, in order to give these lengths along the different axes, you're going to need the axes. You're going to need what's called a basis, and you could cover topics that involve bases in a more detailed manner if you take a class like linear algebra. Here, all you need to know is that, of course, we'll be using the traditional x and y axes for a basis. So we take each of these lengths, u1 and u2, and we write it in terms like this. So we have these angled brackets and u1, which is traditionally the x component, and u2, which is traditionally the y component. Here our vector u is represented in the component form. It has a length of 7 along the x-axis, and along the y-axis it has a length of 3. Well, how do you go between the geometric representation and the component representation? We could use these formulas that you see here. The angle that we have for this vector 7, 3 is 66.8 degrees. So the angle that u makes with the positive x-axis when we wind counterclockwise is 66.8 degrees, or which we'll use this more commonly in this class, radians, 1.166 radians. And so we could take the vector 7, 3, find the magnitude, okay, using this formula. This is how you'll find the magnitude. You just literally plug in the 7 into the u1 place, square it, so you get 49. And then you take 3 and square it, you get 9. And so you'll get that the length is the square root of 58. To get the angle, you could use this formula here. Tangent theta is equal to u2, which is here the y component, all over the x component. And here you have to be a little careful about which angle you're finding. Okay, so because we know that theta is the angle between the positive x and the vector, then we knew that taking this y over that x is going to give us the angle that we want, theta. But if we wanted, for example, to find the angle, let's say beta up here, then we would have to actually use tangent theta is equal to u1 all over u2. So, you have to be careful when you use this formula. You have to know what you're actually finding. On the other hand, we could go from the geometric representation to the component representation. And this is what you typically do when you want to add vectors. You break it up into its components and you add. So to go from the geometric representation to the component representation, you take the magnitude, and we want the length along x, okay? We want the length along x, so we multiply by cosine theta. Why? Because cosine theta is adjacent over hypotenuse. Okay, so that would give us then what's adjacent, which is right here, all over the hypotenuse, which is the length of the actual vector. And so you would have cosine theta is equal to the adjacent again, which is u1, all over the whole length of the vector u. The length of the vector is the square root of 58, and our angle, which we're given since we are talking about the geometric representation, is 1.166 radians. And if we plug these values into this formula here, you will get 7. On the other hand, to find the u2 instead of the u1, you would use sine, right? Because now we'll have opposite. So opposite this angle is over here, which is u2, all over the hypotenuse. So that's how you go between the geometric and component representation. And these are the common ways to express vectors. Well, what are some things that we could do with vectors? One thing we could do with a vector is multiply it by a number. That's called scalar multiplication. What's a scalar? It's just it's a number. A scalar is a number along the real axis. So -5 is a scalar, -2 is a scalar, 73 is a scalar, pi is a scalar. All of these are scalars. They're just good old-fashioned numbers. And we could take a scalar c and multiply it by our vector. And how would that look when we're doing it in component form? We just take the number c and multiply it by the x component, or u1, and we also take the number c and multiply u2. Let's take a look at an example here. Here we have the vector u given as 3, 2. So it has an x component of 3 and a y component of 2. What happens when we take u and multiply it by the scalar 2? Well, you're going to get 3 times 2 equals 6, and you're going to get 2 times 2 equals 4. So 2 times u is the new vector 6, 4. So what does scalar multiplication do to a vector geometrically? Well, if we have a vector u here, which is in black, so here's the vector u, and we multiply it by the scalar 2, we're going to get another vector that has the same direction as u, but twice as long. Okay? If we multiply it by a half, we get another vector, 1/2 u, which is half the length of u, but still in the direction of u. We could also multiply by negative numbers. Okay? Here's -1/3, for example. And what that does is the minus sign causes the vector to flip its direction, and the 1/3 will decrease the length of u by a factor of 1/3. Okay? -1/2 u would look like this vector here in length, but actually point in the opposite direction. So if we wanted to find -1/2 u, it would look like this. So again, what does scalar multiplication do? If the scalar is negative, it will flip the direction. Okay, so that'll point the opposite direction of the vector. And the magnitude of the number will increase or decrease the vector's length proportional to what that scalar is. So if that scalar was 2, you double the length. If the scalar is 3, you triple the length. If the scalar is 1/4, then you decrease the length of the vector by a factor of 4. So let's go ahead and actually compute what -1/2 u would look like. Well, we're going to take a look at the definition here of it. So that we'll take the constant minus 1/2 and multiply it by u1. What is u1? It's 3. And we'll take the scalar minus 1/2 again and multiply it by u2. And so you'll have this vector here, and then we could simplify it and get minus 3/2 or minus 1.5 and minus 1. And that makes sense. So now this vector here is minus 1/2 u. We drew it that way. And it would have an x component here. The x component would be minus 3/2. So its x component will have a length of minus 1.5. And the y component, which is right here, is going to be minus 1. And that makes sense since this vector is pointing to the left and pointing down. So some useful definitions to consider. Vectors are equal when they have the same components. In other words, they're equal when they have the same magnitude and same direction. That's pretty intuitive. And they're parallel when they may be written as a scalar multiple of the other. So, for an example, all of these vectors are parallel. We started out with the vector u and we started multiplying it by different scalars to get the subsequent vectors. So all of these vectors are parallel to each other. And yes, they're also parallel. We consider them to be parallel when it points in the opposite direction as well. So the vector minus 1/2 u is parallel to this black vector u. We consider those all parallel if you could take a scalar multiple and multiply that vector to get the subsequent vector. So all of these are considered parallel. We don't make a distinction between parallel and anti-parallel. For example, you might have heard the concept of anti-parallel, and that would occur if you get a vector in the opposite direction. So we don't make that distinction. We only talk about all these vectors as parallel. Another operation we could carry out on vectors is vector addition. Okay? And here's how we define it. If you have a vector u and a vector v, and u has the x component u1 and v has the x component v1, and u has the y component u2 and v has the y component v2, well, adding these two vectors gives you another vector, the vector u plus v, where you took the x components and added it together and the y components and added it together. So take a look at u and v over here. U is the vector with x component 2 and y component 3, and v is the vector with x component 4 and y component 2. Well, u plus v will be 2 plus 4 because we added the x components there. So this 2 came from here and this 4 came from here. And so we get a new vector with x component 6, 2 plus 4. And the y component, you take that 3 and the y component of v is 2, and you add the y components together. And so u plus v is the vector 6, 5. So what's the interpretation of u plus v? Here I drew out all the vectors, okay? And they're all coming out of this common origin, okay? So here's u, here's v, and here's u plus v. This is just writing them out, but we could interpret these in a different way. If you move the tail of v to the end of u, you will get this vector here. On the other hand, if you move the tail of u and put it at the head of v, you will get the vector there. And notice that u plus v is basically the vector that you would get if you take the tail of v, for example, and connect it to the head of the vector u once you attach the vector u to the head of v. Or you could have thought about it in another way. You could have taken the tail of v and put it on the head of u, and the vector that you would get when you draw a line from the tail of u now to the head of the green vector is the vector u plus v. So that's the common way that you might have encountered of adding vectors, is drawing them tail to end. Some people also call the way of adding these vectors the parallelogram rule, since you get a parallelogram if you attach these tails to ends of the vectors, either u then v or v then u. And either one results in the same u plus v once you go from the tail of one of these to the end of the second vector, either the green or blue, whichever way you chose to add them. Now let's take a look at a deeper reason of why that's working. So how can we reconcile just adding components to actually getting this tail to end rule? Okay, and I called the end sometimes the head, so either one would work. Well, here is the x component of v right there. Okay, the x component of u is right here. Okay, so what happens when I take the x component of u and add it to v, which is the exact operation of taking 2 and adding to 4? Well, I could shift then this x component of u that I drew there to just the end of v, and here we have now the x component of u. And so that is why the tail to end rule works. I mean, we could do the same thing with the y component. Here is the y component of u, and the y component of v is this, but when you add component to component, you translate this up to here and add it. So you'll have this y component there. And so that's how to reconcile these two pictures. You are really just taking x components and adding, and y components and adding, when you attach a vector tail to end. Another thing we could do with vectors is subtract them from one another. Now, we could think about this as a whole new operation where you take u minus v to equal the x component of u minus the x component of v, and the y component of u to be the and subtract the y component of v from that, and let both of those, let that difference be the y component of this new vector u minus v. Or you could have thought it another way. But before getting into that other way, let's just do this straightforward subtraction. So here we have u is equal to 2, 3, and v is equal to 4, 2. So you'll go 2 minus 4. So you take the x component of u, and that's where you got that 2 there. And you take the x component of v, and that's where you're getting the 4 over there. And you subtract these two, you get 2 minus 4. That's negative 2. You do the same thing with the y components, okay? And you'll get 3 minus 2, and that gives you 1. Now, if we are to plot these 3 vectors, here's u, here's v, and here's u minus v, okay? Now, you could have also viewed u minus v in a different way. You could have viewed it as the vector with its tail at v moving to the end of u. So you put the tail of u minus v, so this is u minus v. You put the tail at the end of v, and you put the end of u minus v, the red vector that I just drew, at the end of u. Okay? So it's important which one is being subtracted from which, because on the other hand, if we had v minus u, then this vector here would have been flipped in a different direction. So if we had v minus u, it would have been in that direction. So it's important which is being subtracted. It's not like the addition rule where it's commutative. Of course, with subtraction, it's not commutative. U minus v is not the same as v minus u. Although they have the same length, they won't have the same direction. They would have opposite directions. Now, did we really need to define a new operation for u minus v? Not really. I mean, consider this. So you could view u minus v as u plus negative v. Okay? We already defined vector addition, and we already defined scalar multiplication. Here we're just taking a scalar minus 1 and multiplying it by v. You could view this as an implicit 1 over there. So you're taking negative 1 and multiplying it by v and then adding it to u. That is the same as u minus v. Well, let's take a look by using this tail to end rule. So what then is minus v? Here I'll use, say, pink for minus v. It's going to be the vector that points in the opposite direction of v but has the same length. Okay? And now, what do? We take tail to end, right? When we add the vector. So this here in pink was minus v. Well, what's u plus minus v? Well, that's going to be taking the end of minus v, which is right here, take the end of it and attach it to the so how would that look if we added it out? Well, we're going to get minus v over here. This will be minus v. It's just taking the vector v and flipping it, right, in the opposite direction. And then how do we add? Well, we could take the tail of minus v and attach it to the end of u. If I do that, I'm going to get the vector drawn like this. So this is taking the tail of minus v and attaching it to the end of u. And notice what we get then if once we draw the once we start at the tail of u and go to the end of minus v, as we do when we add vectors, we're going to get this guy over here. Okay? Well, that's just u minus v. So that just gives you another, way to view vector subtraction. It really was not an additional operation. You don't have to think about it as a whole new operation. You could have viewed vector subtraction as the operation of addition and scalar multiplication with a minus 1. Let's now take a look at vectors between points. Okay? Suppose you have the point P over there and the point Q over here, and you want the vector that has its tail at P and its end at Q. Okay? How do you get that vector? Well, here it is. Here's how we define it. So we begin at P and end at Q, and we write that arrow above it to indicate it's a vector. And it's defined this way. You take the x component of the point Q, okay, and it's written opposite. So Q comes second over here, but it's the first thing that you use when you want to actually compute the vector between 2 points. So be careful. That's a common, thing to get slipped up with. So you'll get xq minus xp for the x component, and for the y component, you get yq minus yp. So here's a little example. If you have the point P, which is 1, 2, located right there, and you have the point Q, 3, 3, located right there, and you want the vector that starts at P and ends at Q, well, you take the x component of Q, which is 3, and you plug it in there, and then the x component of p, which is 1, and you plug it in there, and that's where you get 3 minus 1. Okay? And we do the same thing with the y components. Okay? That's where you get 3 minus 2, and you'll have a y component of 1. And that's the vector PQ right here in blue. Now, I want you to be careful because we're not drawing the vector anymore, starting from the origin. But truly, all vectors do start out at an origin. I mean, even if we draw it out like this, this is point space. The black here, these black axes are point space. The purple is at the vector space where the vector is living. Now, just because I drew that vector out here in point space doesn't mean that it's not sticking out of an origin in the vector space. Okay? So it's very common not to see that these purple axes that represent the vector space origin, and to just draw the vector PQ on the point space, but that could lead to some confusion. I mean, imagine I ask to add the vector, say PQ, to a vector here. Say here's the point R, and say here's the point S, and so we get another vector here. That vector there is the vector RS. Starts at R and ends at S. Can you add the vector PQ to the vector RS? Now, if you're just thinking in terms of the tail to end business of adding, you would say no, because the R is not at the point Q. But if you view these as all originating from this sort of common vector space origin, then you can. I mean, PQ would just be poking out like this. That would be PQ. We have it here coming out of the purple axis, and you have the vector RS pointing in the direction here, and then you would be able to add them. So the book makes the distinction and talks about the vector coming out of the origin as in standard position. Okay, it calls it standard position or standard form. Really, just keep in mind that even if you draw a vector not pointing out of the origin, there is some type of origin out there, and that's where the vector actually lives, even though we could draw it on the point space. Okay? And that's just to not get confused with adding vectors and subtracting vectors. That could cause some confusion. And notice up here that I always drew them coming out of the origin. And only when we wanted to kind of interpret geometrically what's going on did I move them tail to end. Here also, everything's coming out of the origin. Okay? So let's now talk about unit vectors. And what's a unit vector? A unit vector is just a vector with length 1 or magnitude 1. That's it. That's what a unit vector is. Nothing too complicated. We have certain special unit vectors. That's this vector here that I wrote as I. This is an I. And this symbol here is a hat. I'll be using hats for all unit vectors. Here we have another special unit vector, j hat. Now, what is I hat and what is j hat? Well, I hat is the vector 1, 0. Indeed, it does have length 1. And here's how it looks over here on the graph, okay? And j hat has an x component of 0 and a y component of 1, so it does have length 1. And you draw it. This is how it would look if you plot it. Now, what if you start with a vector that's not a unit vector, but you want a unit vector that points in the same direction as the vector that you started with? So here I give you v. V does not have length 1. It's longer than 1, actually. Here's v. If we plot it, and it is actually longer than 1. Suppose I want to get a vector v hat over here in red there, that is in the same direction as v but has length 1. How can I do that? How can I take any vector and get a vector of length 1 in the same direction? Well, we could use this formula here. Okay, so we could use that formula right there, and you just take the vector and you divide it by its magnitude. Okay, and dividing by its magnitude, what operation is that? What allows us to divide by a magnitude? Scalar multiplication. Okay, you could look at division as, so you could look at v, you can view v divided by the magnitude as actually multiplying this constant or scalar 1 over v times v. Okay, so that's the operation that we're doing. This will result in a vector of length 1. So here, let's take the example of the vector v. We have 4/3 and 1. That's our v. That's what's above there. And we're going to divide it by the magnitude. What's the magnitude? Well, the magnitude, we have that formula all the way up here. We talked about that formula. That's how you get a magnitude of a vector. And so we take the magnitude, which is the square root of 25 over 9, or 5/3. Okay, so 5 divided by 3 is the magnitude of this vector. And you then will, take this x component and divide it by 5/3, or you could think about it as multiplying by 3/5. And you do the same thing with the y component. And you end up getting the vector v hat. What's the vector v hat? The vector v hat is right here, okay? And you could see this circle here. I took a compass and drew just a perfect circle of length 1 there. And this also works in reverse. If you start with a vector that's shorter than 1, and you divide it by its magnitude, which will be less than 1, then the resulting vector will get longer and will have a magnitude of 1. So all the vectors we were talking about were in the plane, in the sense that they were in R2, okay? But we could have vectors in 3 dimensions, which is R3 there. We write them out like this, so you just have an extra component. Scalar multiplication is defined in much the same way. You just have this extra component there. The magnitude, you just have that extra factor in there. Addition works the same way. Finding a vector between 2 points p and q works the same way, except now you have this z sub q minus zp. And you get the same way to find a unit vector. So everything is pretty much the same when you're working in R3 as far as components. Of course, geometrically now we're going to need an x, a y, and now this extra z-axis there. And what you see here is a sphere. And suppose you want to get the equation of a sphere centered at the point ABC with radius r. We'll have this equation here. But don't just memorize it. Try to think about why that makes sense. Why does it make sense to for the equation that you see above to be the equation of a sphere? Well, think about a vector that starts at the origin and goes to ABC. And think about, say, a point on the sphere. Say we have this point here. Let's just call it XYZ. Okay? And let's draw our vector up to that point there. Now, what's the vector XYZ minus the red vector ABC? And again, here this is the vector ABC. You could view it as the vector ABC. Well, from our interpretations above, we have to take we're going to get a new vector that'll point out like this. and this will be x, y, z minus a, b, c. Okay? Well, what is that? That's going to be equal to x minus a, y minus b, and z minus c. Now again, pause for a second and think about this. What are we going to do to tell the point x, y, z? You need to stay on the sphere. You need to stay on this the edge there. How can you tell it mathematically to stay there? Well, you would take this vector, which is always the difference between the blue and red, and you say, well, I want this vector, I want its magnitude to always be equal to r, the radius of the sphere. If we respect this, then our green vector, okay, that points from the center of the sphere to any point along the sphere, by definition, that means you're a distance r away. That's how you get a sphere, is to be a common distance away from that center. And if that common distance is r, well, then here is how we could respect staying on the sphere. So this equation here is what gives us the sphere. And this equation here is just what you see above here, but square rooted. Okay? So that's that equation there. You would get it by just square rooting the above, and there's no need to take the positive root of both sides. They give you the same exact set, which is the sphere. We also have simple planes. Let's clear out this real quick. So you can pause these videos if you want to take a closer look, but let's erase. Okay, so what about planes? So we have then this for a plane. You say, what, x equals a is a plane? Well, not really, right? We're just drawing it like that. But what we mean when we write x equal a, we mean the set of points x, y, z such that this colon there means such that x equals a. Okay? And here we have a. Okay? And so what does it mean to be a point x, y, z such that x equals a? Well, you don't put any restrictions on y and z. Y and z could be whatever they want. No problem. But x better be a. So that means you're taking this slice up here. It's kind of difficult to draw in 3 dimensions. You could do something else. Say, let's take a look at z equals c, for example. Then what does z equals c mean in 3 dimensions? Well, it means really the set x, y, and z such that z equals c. And you could think about a, b, and c as just numbers, right? I didn't fix them to anything. But if it makes you more comfortable, you could think about it as, say, z equals 1. And then instead of c here, we would just write 1. And what does that mean? What does this set mean? It means, well, x and y could be whatever they want, but z better be equal to c. Or if you were, chose 1, c equals 1, then z better be equal to 1. How does that look? Well, again, x and y could be whatever they want. So along this blue that you see here, that's kind of slicing that sphere in half horizontally, anywhere along that blue, what's true there along that blue? That z would equal c. Any point that you take on that plane, z equals c. And what about xy? Well, xy, which notice they're, these are the x and y axes, they could be whatever they want. So that's why writing just z equals c gives you what's called a simple plane. Now you might say, okay, well, you got them to slice horizontally, vertically, and, but everything is just kind of, you're not slanted at all. We'll talk about how to discuss planes that that are not simple. They're not given by just x equals a, y equals b, or z equals c. We're going to talk about that later in the class.